Welcome. Uh, Welcome to AP Chemistry 1.3, 1.4. Okay, today we are going to look at the elemental composition of pure substances and composition of mixtures. First, identifying understanding what is the difference between pure substance and mixture. A pure substance always contains only one type of atoms or molecules or any formula unit. Okay, so if you take any element like sodium, there's only sodium atoms. There is no other atoms present. If you take molecules, if you take sugar, you have only sugar molecules. You take a formula unit. Usually the ionic compounds, we call them as formula units. Take sodium chloride are nothing but pure compounds. That means there is no impurities. But when you take mixture means two compounds. So if you take glucose in water or salt in water, that means there are two components. There are the two compounds there. It's very easy. But understanding this, you have to have an idea about what is called as the law of definite proportion. That means if you take two pure samples of the same compound, they will have the same proportion of each element by mass. So if you take water from two different sources in New Jersey or from Texas or from other parts of the world, the formula of water is going to remain same. It's going to be only H2O. It is not going to be different. And the percent of hydrogen that is contributing is going to be only 11.2%. And oxygen is going to be only 88.8% in a single molecule, right? So it's not good. That means it's not going to change the molecular formula itself, like H3O or H7O something. So in this unit specifically, we are going to look at key problems. Okay, some of the problems are very easy. Some of the problems are a little bit tricky. So first is to understand how to do mass percent. Mass percent means the percent of the individual elements. So if we take water, the molar mass of water is 18 grams per mole. So you simply multiply 2 times 2 into 1.01. That is coming from the periodic table. And 1 oxygen, 1 times 16 is 16. Roughly you have 18 grams per mole. So if you have to find out only for hydrogen, you will take the contributing factor of only hydrogen. So it is going to 2 hydrogens. Each is 1.01 divided by the overall. That is 18. This is a molar mass. So it is going to be 2 divided by 18 times 100 will be 11.2%. That's what I told. Same thing for oxygen. So that is 16 grams. So 16 divided by 18 times 100 is going to be 88.79%. So if you add both of them, you're going to get 100%. So if you do one more problem, what is the mass percent of oxygen in aluminum sulfate? You have 2 aluminums. So 2 into 26.982. This value is coming from periodic table. 3 into sulfurs. If something is in parentheses, you have to multiply them. So there is 1 sulfur, but there is a 3 outside the parenthesis. So 3 sulfurs and you have 12 oxygens. Okay. You should understand this very clearly. You have 2 aluminums, 3 sulfurs and 12 oxygens. So you calculate the molar mass, and the molar mass is going to be 342.144 gram per mole. So if you have to find only the mass percent of oxygen, what is the contributing factor is 192 grams. So you take 192 divided by overall 342.144 times 100 is going to be 56.11% of oxygen is going to be there. Half of them is roughly oxygen in this one. So if you understand these two things, you can try this problem. What is the mass percent of each of the element in this compound? Eliminate FeTiO3. If you do it correctly, you will end up with 36.81%, 31.56%, and 31.64%. You have to try these problems to make sure that you understand the concept. Okay, this is very important. Second is let's look at one of the simplest formula, but simplest problem. But you have to convert the units. Let's take there is a tablet, and in this tablet you have the overall weight of the tablet is 0.205 gram. And the vitamin E constituent is 0.035 milligram. What is the mass percent of vitamin E? So the overall weight mass is 0.25. So that is going to be in the denominator. But one is given as grams and one is given as milligram. So either you have to change both to milligrams or more to grams. So what we are going to do is going to change these things into milligrams into grams. So 0.00035 grams, right? Divided by 0.305 gram. Okay, 1 gram is 1000 milligram. So that is 0.017% of vitamin E is there. So this is very simple problem, but you should be careful about what is the unit that is given in a problem. Okay, units are very important. You cannot just take two numbers and divide them. Third is the using ratios. A sample of dichromate has some impurities. It is found that K plus makes up 19.24% of the entire sample, and all the K plus comes from the dichromate compound. Find the mass percent. So he says there is a sample of dichromate. This contains some impurities, but K plus makes up 19.24%, and all the K plus comes from the dichromate compound. That means the cation is pure component. You have only a dichromate impurity. You have only the Cr2O7 2 minus impurity is there. Okay, it is not the potassium impurity. So if the potassium is pure, if the pure potassium 19.2% is going to react with the corresponding anion to make sufficient amount of pure potassium dichromate in this mixture. Okay. So first, to find out, you have to calculate the overall mass of molar mass of potassium dichromate. There are 2 potassiums, 2 chromium, and 7 oxygen. You use the same method that we calculate how to calculate molar mass, and then find out the molar mass is 295.983. All these values are coming from the periodic table. And then you take 17.9898 grams is the pure component, right? All the K plus makes up 19.24%. So 17.9998 gram is in 295.983 gram. In 295.983 grams of the overall substance, this much is potassium. But that much potassium is 19.24%. Then what is the overall percent of potassium dichromate? Okay, it might look a little bit tricky to do these ratios, but you should be careful about how to do this. It's a very simple ratio. And you divide and multiply by 19.24 to get 71.99%. Okay. So try to understand these kinds of problems. Next is to understand what is the difference between a molecular formula and empirical formula. A molecular formula means complete formula. Empirical formula means simplest formula. Okay. So if you take hydrogen peroxide, if we say that is a molecular formula, we can empirically make a simplest formula by dividing these by 2 to get HO as the empirical formula. This is the simplest formula. C6H12O6 can be written as CH2O. That is the simplest formula. C2H6 can be written as CH3. But if you take water, one number is odd. You have a 1 and a 2, odd and even. So it is going to remain same. You cannot divide any of them. So the molecular formula and the empirical formula are the one and the same. So what is the meaning of that? So let's take this example, CH2O. In the CH2O, it is the simplest formula. It is base n. That means the n can be any integer. If n is equal to 1, then it is going to be the formula of the substance is going to be CH2O. When n is equal to 2, it could be C2H4O2. When n is equal to 3, it can be C3H6O3. So the n can be any integer starting from 1 to n. So anything can be there. That means the empirical formula is the source from which any number of different molecules can be formed. So let's look at the problem. Calculate the empirical formula and the molecular formula for caffeine. Okay. So the caffeine is said to contain 49.5% carbon, 28.9% nitrogen, and 16.5% oxygen, and 5.1% hydrogen. So It is given that in caffeine there is 4 elements: carbon, nitrogen, oxygen, and hydrogen, and these are the varying percentages. If you add all these percentages, you get 100%. That means if you have 100 grams of a substance, I'm going to have 49.5 grams of carbon, 28.9% of nitrogen, 16.5% of oxygen, and 5.1% hydrogen. So step 1 is to take each of these in grams, and then 1 mole of each substance, you are converting the grams into moles. Okay. So for 49.5 grams, 1 mole is 12 grams. This is coming from periodic table. So you'll get 4.12 mole. Nitrogen is 28.9 gram. 1 mole is 14.06. You'll get 2.06. Similarly, you solve for hydrogen to get 5 moles, and for oxygen, you will get 1.03 moles. So you converted everything from grams to moles here. This is the first step. The second step, divide using the smallest value. Why we are dividing using the smallest value? Because we are finding the empirical formula. Empirical formula is nothing but the simplest formula, right? So 1.03 is the smallest value out of these 4. So take each number, moles, 4.12 divided by 1.03, 2.06 divided by 1.03, 5 divided by 1.03, and 1.03 divided by 1.0. So you will get 4 carbons, 2 nitrogens, 5 hydrogens, and 1 oxygen. This is the empirical formula, C4H5N2. Usually you write carbon and hydrogen first, and then the heteroatoms like nitrogen, oxygen, other atoms later on. So if you write nitrogen in a different order, that's fine too. So you can calculate the empirical formula mass now. So 4 into 12 is 48, 1 into 5 is 5, 2 into 14 is 28, 1 into 16 is 16. So roughly you get a value of 97 grams per minute. This is a rough mass. Now, if the real or the correct molar mass for caffeine is given, so then you can find the factor that is called as N now. So you have the correct molar mass is 194.2 grams per mole. So if I have the empirical formula mass, which is the smaller one, if you take the higher number and then you divide by the smaller number, you will get that ratio, that you will get the value N. If you take that N and you multiply to the empirical formula, you will get the correct molecular formula. So this is the empirical formula of caffeine, but this is the molecular formula of caffeine. So that means when N is equal to 2, that is caffeine. When N is equal to 1, it is not caffeine. Okay, when N is equal to 2, it is caffeine. Okay, there is an empirical formula of that substance. But when N is equal to 3, it is not caffeine. Okay, so this is when it changes, it is not caffeine anymore. So this is the correct constituent C8H10N4O2. Okay, so you should understand that very clearly. So the first step, we said you take the grams and convert it to moles. Use the smallest number to identify the correct number of atoms inside the empirical formula, and then you write the empirical formula. The empirical formula, you calculate the empirical formula mass. If the empirical formula and the molecular formula has the same mass, then you don't have to worry about it. But if the molar mass of the correct formula is different, then you divide and then get the ratio and then multiply to get the final answer. Next problem is to understand what is called as the combustion analysis. The combustion analysis is a next method where you take any sample, usually an organic sample, and then you heat with oxygen and you convert them into water and carbon dioxide, and you absorb them using an absorbent, and then you weigh them. Based on that, you can find the empirical formula of this compound, and also you can find the molecular formula also. So let's take, if you take 2.04 grams, this unit, you said you can dismantle this unit. This unit contains water absorber, and then you have a carbon dioxide absorber. So usually magnesium chloride and sodium hydroxides are used. So you take this whole thing, this entire unit with the pure good absorbent is 10 grams. The other one is also 10 grams. You take the sample and you ignite with oxygen, and then the reaction continues to form carbon dioxide and water and a little bit of other gases, which is negligible. If that happens, you cool it, and then you take it, dismantle, and then you weigh it to see how much water was collected. So when you weigh, you see 12.4 grams of this unit, and then you get 14.48 grams of this unit. That means you can subtract to find you have 12.4 grams of water and 4.48 grams of carbon dioxide. So now we got the value. We know that the compound that we are using has carbon, hydrogen, and oxygen based on analysis. But we don't know the exact empirical formula. 2.04 grams gave 4.48 grams of carbon dioxide and 2.4 grams of water. Earlier in that example that we saw that the caffeine, we saw that the percentage of carbon, nitrogen, and oxygen were given, and hydrogen were given. These were the individual elemental percentages. But here in this problem, in this, what did we get? We get only carbon dioxide and water. Now we have to convert this carbon dioxide and water into grams of carbon, grams of hydrogen, and grams of oxygen. How do we do that? You take 4.48 grams of carbon dioxide. 1 mole of carbon dioxide is 44.44 grams carbon dioxide. This is coming from periodic table. 1 mole of carbon dioxide has 1 mole of carbon because there is 1 carbon and 2 oxygens. So 1 mole have 1 mole. 1 mole of carbon weighs 12.01 gram. That also comes from periodic table. So these two values comes from periodic table. You write it in such a manner. Okay, so when you write ratios, you can cancel it. Grams, grams, mole, mole, mole carbon, mole carbon. The answer must be grams carbon. Next, you found out for carbon, you find it hydrogen, 2.4 grams of water. 1 mole of water is 18 grams. 1 mole of water has 2 moles of hydrogen because there's 2 hydrogens. 1 mole of hydrogen is 1.01. Now you have 0.27 grams of hydrogen. Since with the elemental analysis, we know that we have only carbon, hydrogen, oxygen. Since we found out both carbon and hydrogen, we can subtract from the initial one. Initially, we have 2.04 grams. So 2.04 minus 1.22 plus 0.27 will get 0.55 grams of oxygen. You don't have to recalculate this. So we know what is the grams of this. So you do the same thing now. Like the previous problem, you take the grams, divide by the molar mass to get the number of moles. So grams to moles for each one of them, 1.22 divided by 12, 0.27 divided by 1.1, 0.55 divided by 1.6, you will get the number of moles. The next is the most important step, divide by the smallest number. Out of these 3, 0.034 is the smallest number. So what do you do? 0.12 divided by 0.034, 0.27 divided by 0.034, and the same thing will give you 1. So the empirical formula is going to be C3H8 and O1. So this for hydrogen, you got 7.94. So I can round it to 8. But if you get 7.5, then you have to multiply that value by 2. Okay, so you should be very cautious. So you cannot round that to you cannot round 7.5 to 8. Okay, you have to multiply that by 2. So if you understood this concept, you should be able to do a couple of problems. So look at this problem. Okay, read this carefully. You can stop screen and look at this problem. If you do understand this problem, you should be able to get these answers given here. Okay. And that should be helpful because these are good AP level questions. The second one is this one. This is a multiple choice question. Okay, you can try this one. I will put the answer in the video description. Okay, you can think about it and then you can look at the answer. The third one is the emerald are composed of 4 different elements. So now you do element analysis and you found out that this much beryllium, aluminum, silicon, and oxygen are there. Here he specifically says the empirical and molecular formula are the same. That means you don't have to find out the identifier, right? So you don't have to find the integer here. So you just calculate the empirical formula and find the molar mass. If you do this correctly, you should also end up with this answer. Okay. So this is a very important 1.3, 1.4. Many multiple choice and open-ended response questions might come. So you should understand this concept very clear. Okay. We'll see you in the next session.